This is Mr. Pillar, Modern Energy, ECET273, lecture number 9. We're going to talk about motor action, and particularly AC synchronous machines, based on Chapter 10 of the Square DeWitt text, Chapter 4 of the Fardo-Patrick text. So motors convert electrical energy into mechanical energy, create rotary motion. The electrical motor load is the major power-consuming load of the electrical power system. Motors of various sizes are used for various purposes. Large industrial machine operation all the way down to toys and household appliances. So as opposed to two major loads in America, the motor and lights. So we're talking about motors here. We originally talked about generators. Motors again are rotating machines. Same construction as a generator, same principle. Faraday's law is causing motor action to happen, but instead of putting mechanical motion on the shaft to pull electrical energy out of a generator, we're putting electrical energy into the armature to pull mechanical motion off the shaft. Remember, generator action is brought about by a magnetic field, a set of conductors within the magnetic field, and the relative motion between the two. Motion is similarly produced in a motor through the interaction of the magnetic field and a set of conductors. Like generators, motors have several basic parts in common: the stator, the rotor, and some kind of method of placing the field on the rotor, for example, the brush commutator assembly, or you can have a permanent magnet, or as we're going to learn about the induction motor, we use induction itself. So here is a schematic of a motor. Stator's on the outside. Okay, rotor's on the inside. Rotor is the piece that spins. Stator is the thing that you mount to something. Rotor is attached to the mechanical shaft. This particular layout and design is a DC source. There is a DC voltage on the armature. The armature is on the rotor and has brush commutator. We have field poles, permanent magnets on the stator. This is a DC machine design, but same design goes for all motors. So here you go. There, the top right, we have no current on the conductors. Magnetic field, axis of rotation down the center of the conductors. Remember your left hand, right hand rule. Right hand is going to show you the movement of the motor. The left hand showed you the flow of voltage and current. A little point of schematic design: a dot in the center of a conductor means that current is coming towards you. An X in the center of a drawn conductor means current is going away from you. Imagine current as an arrow. That's the point coming at you. That's the feathers leaving you. Okay? So here, B has current coming at us. A has current flowing away from us. So here on this other perspective, current is going this way and then around out this way. Plus to minus. This particular drawing is using the physics current flow, not the electrical design of conventional current flow. Here, current is flowing because the brush is fully touching on a single slip ring. Here, current isn't flowing because you have plus minus going across the brush, and so that's supposed to have lower resistance than the current along the rotor. Here's a view of the rotor is going to spin in this clockwise direction because current is flowing around this way on the B wire and around the other way on the A wire. If you hold your left hand in a curled format, almost a fist but an open fist, your thumb is the direction of the current. Your fingers wrap around the conductor and show you the lines of flux that are going to flow on the conductor that are going to react with the lines of flux of the magnet. So here, B is coming at you, so your thumb of your left hand points at you, your fingers curl around and point down to the right in a clockwise direction. A turn your thumb the other way with your left hand, and the current is flowing into the page, and the coil, the magnetic flux that's created because of current flowing on that conductor is going in a counterclockwise direction. And so we have an upward motion with the B and downward motion with the A, opposing the magnetic flux of the permanent magnets. So when we talk about motors, one of the motors that we're going to talk about is a synchronous machine. We can talk about it as a single phase. Three-phase has the same characteristics. Single phase is just slightly simpler. So a single phase synchronous motor has stator windings that are connected across the AC line. The rotor is made of a permanent magnet or an electromagnet material. Once the rotor is started, it rotates in sync with the revolving stator field. So the field on the stator we're going to be in complete sync. So if you have a 60 hertz current, and you'll have a 60 hertz current on your rotor. Here's another drawing of a synchronous machine. We call this a two-pole. You have the this eye here is the rotor, and that's two poles, north and south. So there's two poles on this machine. Poles come in even numbers, 2, 4, 6, 8. We're going to talk the next couple slides about that. But again, I want to show you we have slip rings on this field winding. Field winding is in the middle. Stator is on the outside. The armature is on the stator. The field winding is on the rotor. So this is a rotating field layout. Okay, so a synchronous machine has one speed and one speed only, and it's dependent upon the frequency of the current that's going into the machine and the number of poles. The calculation of the speed of a synchronous motor is based on this speed formula. NS, which is your synchronous speed in RPM, is equal to 60 times the frequency divided by the number of poles divided by 2. So a two-pole machine with 60 hertz frequency in America, that's the frequency we use, is 3,600 RPM. A 4-pole machine will be 1,800 RPM. A 6-pole machine, 1,200 RPM. 8-pole machine, 900 RPM. 10-pole machine, 720 RPM. 12-pole machine, 600 RPM. It locks these in. There's nothing we can do to change the speed unless you change the frequency of the current. So since synchronous machines are more costly than induction motors, and they're more costly because there's more parts to it. You have slip rings. There's maintenance issues. Because you have slip rings, you got to change the brushes. Synchronous machines are used basically for loads that require constant speed and power factor correction. An interesting piece of a synchronous condenser, the power factor of a motor can be adjusted by varying the field current on the synchronous motor. The field is the magnetic current that the armature current is affected by. We can actually make the field current cause the motor to have a leading power factor, and in that case synchronous motors can be operated with no load, meaning that there's no mechanical load on the shaft, and lay it out with a leading power factor. Machines built for this purpose may not actually have a shaft that comes out of the machine that you can mechanically tie to. The magnetic field is generally set up by a DC current, so we can vary that DC current. We know how to control that, and we can vary that DC current and adjust our power factor correction as we need, as power factors required across the board.